In this video, I will show you how a simple equation produces one of the most iconic mathematical objects, the Mandelbrot set. I'll also explain exactly where all of these beautiful colors come from. So let's get to it. The first step in generating the Mandelbrot set is to begin with the function f of z equals z squared plus c, where both z and c are complex numbers. The next step is then to follow the simple rule of starting at z equals 0 and iterating or repeatedly applying the function f of z. Finally, by asking for which numbers does this iterative process remain bounded, the Mandelbrot set emerges. We'll take a look at how this process works algebraically for two simple cases, and then we'll see how it translates to the geometric figure. So let's start by plugging z equals 0 into the function. This gives us 0 squared plus c. Next, we'll choose a complex number c and check if the process of repeatedly applying f remains bounded or goes to infinity. All the numbers for which this process is bounded will be in the Mandelbrot set. The rest will be excluded. The first number we'll choose is c equals 1. After the first iteration, the result equals 1. Next, we plug this result back into the same function and evaluate again. This time, the result is 2. Now, if we plug 2 into the function and continue this iterative process, we can see that the result gets bigger every single time. There will be no upper limit that is reached, and for c equals 1, the function f goes to infinity. Thus, we can conclude that 1 is not in the Mandelbrot set. What about if we choose the imaginary number I? At the first iteration, the result is -1 plus I. The next iteration results in -I. The third iteration goes back to -1 plus I, and the fourth goes back to -I. So in this case, the function f will remain bounded. It will just keep oscillating between -1 plus I and -I. Therefore, the number I is a member of the Mandelbrot set. Okay, so that's the general algebraic process to determine if a number is inside the Mandelbrot set or not. But how do we use this method to produce the notable geometric figure? In order to do this, we need to consider the plane of complex numbers. This plane consists of one axis representing the real part and the other axis representing the imaginary part for any complex number. If we plotted the 2 points we've just analyzed, z equals 1 and z equals I, then they would appear here. And a number like 1 minus I, or -1 plus I, would be here. Now before we begin sorting through all of the points that may or may not be in the Mandelbrot set, we can make use of a very useful fact. Any number that is in the Mandelbrot set has a magnitude less than or equal to 2. So we only need to check numbers inside of this circle. Anything outside of it is guaranteed to be unbounded when going through the process of repeatedly applying the function f of z. Also, since we cannot perform this function an infinite number of times, we can make use of this fact to check at each iteration step whether the result is in the circle or not. And as we perform more iterations, we will approach a better and better approximation to the true Mandelbrot set. At the first iteration step, all of the numbers inside of the circle will be less than or equal to 2. Let's color them yellow. Now we'll zoom in and go through the iterative process. After we perform the next iteration, only the points in the black will remain bounded by 2. The ones in the yellow become unbounded, so they must not be in the Mandelbrot set. Let's now color the black points green. In a few moments, it will make sense to you why we are doing so. If we perform another iteration, again there will be some points that escape beyond 2. The ones that remain bounded are in this black region, and the ones that have escaped are green. Now if we choose to make the bounded points a different color, let's say blue, we can start to see that we can use different colors to represent how fast points escape the boundedness criterion. And continuing this process, by iteration 5, we can already see something that is starting to resemble the Mandelbrot set. Now, for aesthetic purposes, as we continue this iterative process, we'll make the color changes more gradual and continuous. And very quickly, the intricate structure of the Mandelbrot set emerges, where at every stage, all of the points in black are points that remain bounded, while the colors represent how quickly various points escape the boundedness criterion. Remember, this criterion was having a magnitude less than or equal to 2. So there you have it. That's how the Mandelbrot set emerges from the simple equation f of z equals z squared plus c. Be sure to stay tuned for future videos in this playlist where I'll explore interesting questions related to this set, like how are Julia and Mandelbrot sets related, and what kind of structures emerge if you zoom into certain areas of the Mandelbrot set.